So next, let's talk about proxies and load balancers. And these are really big topics to be covering in a single video. But the good thing is we actually already know more about these than you might think. And also as developers and, system designers, we actually don't need to go super in depth into these topics. But if you're interested, I would recommend doing so because it can get pretty interesting, but, pretty complicated and very nuanced. First, let's talk about proxies. There's two main types of proxies. Let's start with forward proxies, and sometimes proxy just implies forward proxy. If somebody just says, proxy, they probably mean forward proxy rather than reverse proxy, but not always, which can get confusing. So if we are clients and we are trying to make a request, to some server, but we have a middle server in between. So this middle server in this case would take our request and then forward it to the actual server on our behalf. And not only that, but it would actually act as a user. It would be the middle layer that would do the work for us. It would actually hide the client from the destination server. So, let's say we make a request that has our IP address in that request, right? We know that's just how the internet protocol works. But having a middle layer is like having a friend that's going to do something on your behalf. Like you have to, send some information somewhere, and then somebody in between, like the mailman or something, does it for you. Maybe that's not the best analogy because, with mail, your address and stuff is still on the envelope. But the idea here is that the middle layer, the proxy, will hide the user and protect their identity. But since this middle layer is handling that traffic, this can be used for other things as well. Like, for example, maybe your country or your computer or, something with your network is not allowed to access this server. Well, but you are allowed to access the proxy server. So what the proxy does is for you, since you're not allowed to directly go to the origin server, you can't do that. The proxy server does it for you. It will go to the server on your behalf and then respond to you. So it'll bypass that restriction. A forward proxy can also block things like on a corporate network or on a school network. It's pretty common to have all devices that are connected to that corporate network go through some proxy. Now, maybe if you try to access some site that you're not allowed to, like sometimes corporate networks will actually block YouTube, which is kind of frustrating, I think. But your corporate network, your corporate proxy could say, hey, you're trying to go to YouTube? Nope, not going to let you do that. All traffic goes through the proxy, and the proxy decides, it sets rules that can block access to certain sites and certain resources. So a real world example of a forward proxy would be, just like a corporate proxy like I talked about, or sort of a VPN, right? That's a very natural thing because VPNs hide the original user from the server. They hide your IP address. You can act like you're from a different country and all that kind of stuff. Now, moving on to reverse proxies. So the simplest way to describe a reverse proxy is that instead of hiding the client or the user, which is what happens with a forward proxy, a reverse proxy actually does not hide the client, but it hides the destination server. Like as a user, we make requests to this server, but this server is actually not the one handling our request. This middle layer, this reverse proxy, is actually taking our request and with all the information that it includes, like the IP address and everything, which it doesn't necessarily have to do, but usually it does. And then it takes that request and forwards it to some other server. And then that server fulfills the request. It goes back to the reverse proxy, and then the reverse proxy sends it back to the client. But the important thing here is that unlike with a forward proxy, the client actually does not even know about the existence of the destination. It just knows that this reverse proxy exists. Everything we do goes through the reverse proxy, and then we get something back. We don't even know about the existence of all the other servers. And the server, though, will probably know about the existence of the client. Not necessarily, but usually that's the case. And at a high level, it's really that simple. Now, what is an example of a reverse proxy that you can think of? Well, we actually talked about it recently, CDNs, right? Do you think a CDN is a forward proxy or a reverse proxy? Well, as users, we directly go to the CDN. Like that's our cache. That's where we're going to try to read data from. But possibly that CDN will make a request to another origin server that we don't even know the existence of, right? And we don't care about it. We just interact with the reverse proxy with the CDN, and then the CDN maybe will go to the origin server, get the origin server, cache the data, and then send it back to the client. But the point is, we don't know about the existence of this. The reverse proxy, the CDN, abstracts this away from us. We don't have to worry about that. Now, another popular example of a reverse proxy is actually a load balancer. That's what we're going to spend the rest of this lesson talking about. Load balancers are very, very important, but luckily for us, conceptually, they are pretty simple, though implementing them would not be super straightforward in the real world because there's a lot of like networking details involved with that. So a load balancer is a type of reverse proxy where a user is going to make requests which are going to hit the load balancer first. But we have multiple servers. Reason being that we have a lot of user traffic that we have to handle. A single server can't handle all that traffic. So we actually have multiple servers, doing the same thing. Let's say all of these are running the exact same application, the exact same API or whatever. What we want to do is horizontally scale the servers, which is exactly what we're doing. And we want to distribute the traffic evenly among all the servers, aka we want to balance the load of, user traffic. So conceptually, that's it. Like that's what a load balancer is for. And in terms of system design interviews, this is pretty much what people mention. And it's almost laughable in my opinion, because, load balancers are super complicated. Yet in interviews or in discussions, we just say, I'm just going to throw a load balancer in front of it and then horizontally scale those servers. Presumably they're implemented with REST, which allows them to be, scaled. They're stateless, let's say. So that's great. And now how exactly do we distribute that traffic evenly? Well, there's many algorithms to do it. The most simple is probably round robin, which as the name implies, we go round robin. We go, in a cycle. The first request will hit the first server. The second request will hit the second server. The third will hit the third server. And then the fourth request will start all over. We'll go back to the first, we'll go back to the second, then the third, and just go in cycles just like that. So this will mean that each of the servers will get an even amount of traffic. Now, a problem could be that one of the servers is less powerful than the other ones. Like we have 100 servers, some of them maybe just happen to be less powerful. In that case, we would have a variation of round robin, which is called weighted round robin. Maybe this server is, a 10 and this server is a 5 and this server is also a 5. Or, in terms of percentages, this server should get 50% of the traffic, this server should get 25%, and this one should also get 25%. So in that case, we would route the requests like this. The first request goes to the first server, the second request also goes to the first server, then the next one goes to the second, and then the next one goes to the third. So since this server is twice as good as the other two, we expect it to be able to handle twice as many requests. So if this one got 4 requests, these other ones would get 2 requests each. Now there's many other ways we could also do this. We could load balance based on the number of least connections. That's another strategy. We get a request and we route it to the server that has the least number of connections. Like with round robin, just because we're evenly distributing the requests, maybe some requests just, take longer to process. Maybe this first request asked for a lot of data, so it takes, a bunch of computation to do that. Maybe even though it was first, it takes longer to process. Like this second request is finished, and then we're making another request. Where should we route it? Well, this server is already taken. It has a connection. So we send that to this server, which does not have a connection. So this is load balancing based on the server that has the least number of connections. So that's another valid strategy. If these servers are located in different locations, we could also, load balance based on user location. Maybe this server is in North America, that's where the client is, so we route the request to this server. Maybe, this server is in Asia, this server is in Europe, and if European users are accessing the site, we route those requests here. Asian users, we route those requests to this server. There's another variation that we'll probably talk about later on, which is called hashing. So we actually take that user request and use some field, possibly the IP address or the actual content of what the user user is requesting, and we take a hash of that, or maybe hash the user ID. We could do anything, but hashing has its own benefits that we'll be discussing later on. I also want to quickly mention, but not go super in depth into this, there are a couple types of load balancers, layer 4 and layer 7. Layer 4 is at like a lower network layer. You can think of this as being the TCP layer. This is the transport layer, and layer 7 is the application layer. You can think of HTTP, like an HTTP server is the load balancer here. Now, the benefit of a layer 4 load balancer is that it's typically going to be faster because all we do is look at the IP address to, determine how to balance. So we could use, location-based balancing, or we could just use round robin. But we can't really be smart because with TCP layer, we don't actually have access to the application data. We can't, decrypt that. We can't see exactly what resource is the user using. So while this is faster, it's less flexible. With layer 7 load balancers, we can look at the application data. Maybe one of these servers is handling certain types of resources. Maybe this server is all about tweets, for example. Maybe this server is all about the user profile, and the third server is all about authentication, or, I'm just making this stuff up, but they serve different purposes. With a layer 7 load balancer, we could intelligently route user requests. We could see a request and see it's based on tweets, it's related to tweets, so we'd route it to this server. Another request could be related to authentication. We'd route that request here. So layer 7 is more powerful, but since it's layer 7, we'd have multiple connections. Like we'd have a TCP connection established here and another one established over here. So it's more expensive because we are going to be decrypting every request and then creating a new request. Whereas layer 4, we'd actually just be taking a request and then forwarding it to another server. We're not doing anything with the application data. We're just taking the IP address of that request, and its destination was this server, but we're going to replace that IP address with one of these servers' IP addresses and just forward it there. And then when we get the response back, we just return that response back to the client. This is a very high level overview. Most likely the distinction between layer 4 and layer 7 won't come up at all, but simply put, layer 7 is faster but less flexible. Layer 7 is slower but much more powerful. Now you might be wondering, if we just have a single load balancer like this one, what happens if this load balancer goes down? This is sort of a single point of failure. Yes, we horizontally scaled our servers, so we increased the availability, increased the reliability. If one of these goes down, it's okay. We can still route requests to these other servers. Load balancers are capable of doing that. But what if the load balancer itself goes down? Well, in that case, the easiest thing to do would be to have multiple replicas of the load balancer. So we'd actually have multiple load balancers, and then user requests would be going to each of those load balancers. Or maybe we just have a backup load balancer, and if this one goes down, then requests would be routed to the other. Typically, load balancers can handle a very, very large amount of traffic and handle really, really high throughput. So it usually doesn't come up that a load balancer would be overloaded because they're not actually doing anything. Typically, they're just forwarding the request to other servers. But if you're really, really interested in load balancers, I'd consider reading a paper by Google. You can search for maglev. It goes a bit more in depth into how load balancers can be implemented. And if you're looking for some open source implementations, the most popular one is Nginx. It's a very popular open source load balancer, and it can be used for a lot of other things as well. It's really, really powerful. There's a good chance you've already heard of it. But in the open source world, if you're going to be implementing your own load balancer, you're probably using Nginx, though it's a lot more easier to just use a load balancer provided by a cloud provider like AWS or GCP. That's much more common because these are, pretty hard to implement because these are really, really powerful. And if you can get it out of the box, that's probably preferred.